Hey guys, welcome back. The main purpose of using a technology like Hadoop is to analyze mass volume of data in relatively short amount of time. However, to get the most out of Hadoop and to use it as efficiently as possible, it is the developer's responsibility to write optimized programs. In this lesson, we'll learn some key concepts, important configuration properties to optimize MapReduce execution. The properties that we will explore in this lesson will come in handy when you're troubleshooting performance issues with your MapReduce jobs. While going over these properties, we'll also talk about the actual symptoms or scenarios to look for in your troubleshooting process so you know when to apply these properties. The first set of properties we will see is related to the memory configurations of mapper and reducer. When we learned about yarn, we saw that in yarn we can configure or request the amount of memory need to run our mapper or reducer. You can configure the total memory or the upper limit in memory that Hadoop will have to allocate to mapper or reducer using MapReduce map memory MB and MapReduce reduce memory MB respectively. So here is a symptom. In your log files, when you see killing container error messages like you see on the screen, it is time to increase the memory settings for either mapper or reducer or both, depending on which task is failing. As we already know, mapper or reducer is a Java process, and each Java process has its own heap memory. And the maximum allocation settings for your heap memory is configured via these two properties that are highlighted. MapReduce map Java ops and MapReduce reduce Java ops for mapper and reducer respectively. If the mapper or reducer process runs out of heap memory, the task will actually throw a Java out of memory. So when you see an out of memory exception in your logs, it usually means you need to increase the value of either MapReduce map Java ops or MapReduce reduce Java ops depending on which process is throwing the error. Since the MapReduce map memory MB and reduce memory MB usually defines the upper limit of allocated memory for mapper and reducer, MapReduce map Java ops and reduce Java ops is configured to a value less than the actual value of MapReduce map memory MB and reduce memory MB. Usually the value of Java ops is 75 to 80% of MapReduce map memory MB and MapReduce reduce memory MB. These are memory configurations for individual mapper and reducer. In Yarn, each application is managed by a process called application master, and the memory requirements for the application master can be different from your mapper and reducer, and you can configure application master's memory setting using yarn app MapReduce am command ops and yarn app MapReduce am resource MB. Yarn app MapReduce am resource MB defines the memory upper limit for the application master. Yarn app MapReduce am command ops defines the maximum heap size of the application master, and its value is usually less than 75 to 80% of yarn app MapReduce am resource MB. Memory is a finite and scarce resource, and there are limits to how much you can request for. The minimum and maximum amount of memory you can request for your mapper and reducer is defined by yarn scheduler minimum allocation MB and yarn scheduler maximum allocation MB. Both properties are set by your Hadoop administrator. Default value for minimum allocation MB is 1 GB and default value for maximum allocation MB is 8 GB. So we can request memory for the mapper and reducer between 1 and 8 GB by default, usually in multiples. And when you see an error message that states that you're requesting memory more than the maximum allowed memory from the resource manager, which usually means that you're asking for memory which is over the maximum allocation MB. So that's the property you need to check when you see such an error message. So far we looked at the memory settings for individual tasks. Let's now talk about properties which we can use to tune the shuffle process. Shuffle is an intense resource-consuming process in your MapReduce execution. Fortunately, there are some useful properties that we can use to tune up the shuffle execution. On the map side, the mapper produces the output. They need to be partitioned to be sent to the appropriate reducers. The outputs from the mapper are not returned to disk, but rather it will be kept in memory until the size of the output reaches 100 MB by default. When it reaches a certain threshold, which is usually below 100 MB and configurable, the output will be spilled to the disk. Any operation that is done with data in memory is faster when compared to the operation which is done with data on the disk. So it is much beneficial to keep the data in memory as much as possible before you write it to the disk. 100 MB is a low value and we can easily run out of the configured 100 MB, especially if the key value pairs are larger in size. So when the key value pairs are larger in size, you will see that the key value pairs will be spilled from memory to the disk. And the sorting operation will be a combination of both in memory and in disk, which is not very ideal and efficient. So it is often a good idea to increase the memory setting. MapReduce Task IO Sort MB can be used to define the amount of buffer memory to use while sorting the files. You definitely want to consider increasing the memory limit beyond 100 MB, especially when it takes a lot of time to start the reduce phase. This means your shuffle process is taking longer. Also, look at the counters of your job execution. If you see a huge number of spilled records, it's an indication that you need to increase this number. The value for this property varies from cluster to cluster, and it totally depends on the kind of jobs that you execute in your cluster. So to come up with the value for this property, you have to test with different values in your pre-prod environment first before you apply any changes to your production environment. Moving on. It is always a good idea to compress the map output. When the job requires a lot of mappers, there will be a lot of data that will be transferred to the reducer over the network. So smaller the data, the better, the faster the transfer. And also the data transfer will take up less network bandwidth. Map output compression can be enabled using MapRed compress map output property, and the compression codec can be set using the property MapRed map output compression codec. We'll talk more about compression in the file formats chapter. As the mappers complete, the reducer will start to copy the individual map output to the reducers. MapReduce reduce shuffle parallel copies property controls how many parallel threads can be used to copy the output from the mappers. The default value for the property is 5, which means you can have at most 5 threads running in parallel to copy the map outputs. This number can be increased when you have jobs with a lot of mappers, or in other words, when you are processing huge data sets, because the more number of mappers, the more threads in parallel will help us copy the data faster. When all the map outputs have been copied to the reducer will start merging the map outputs while maintaining the sort ordering. This merge operation is done in rounds. MapReduce Task IO Sort Factor determines how many outputs from individual mappers can be merged at once. If you have output from 50 mappers and MapReduce Task IO Sort Factor is set to 10, then 10 outputs from individual mappers will be merged in one single round. When you have a lot of mappers, it is wise to increase MapReduce Task IO Sort Factor. Again, you have to test out the number, and it takes a lot of trial and error to get this setting right. And it totally depends on the kind of jobs that execute on your cluster at any given time. So far, we saw some key properties that can be used to optimize MapReduce execution. When you have a job which is executing slower than you expect, go over all the scenarios and symptoms that we went through in this lesson and apply the appropriate property or combination of properties to optimize the MapReduce execution. Let's talk about 2 more interesting concepts before we wrap this lesson. Sometimes you will notice that a job with 3 input splits executed 4 mappers, and Hadoop will actually kill the 4th mapper. The job would still complete successfully, but why did it execute the 4th mapper when there are only 3 input splits and kill it at the end? What you see is called speculative execution. When Hadoop framework feels that a certain task, it could be mapper or reducer, that it is taking longer on average compared to the other tasks from the same job, it clones the long-running task and run it on another node. This is called speculative execution, meaning Hadoop is speculating that something is wrong with the long-running task and runs a clone task on another node. The reason for the slowness in your long-running job could be due to a faulty hardware, network congestion, or the node could simply be busy. There could be many reasons, right? Most of the time, this is a false alarm and the task which was considered long-running or problematic completes successfully. In that case, Hadoop will kill the clone task and proceed with the results from the completed task. In some cases, this is beneficial because in a cluster with hundreds of nodes, problems like hardware failure or network congestion is common, and prematurely running a parallel or duplicate task would be better, since we won't be waiting for the task and problem to complete because it may not complete, right? But in some cases, it is probably expected that certain maps or reduce may run a little longer when compared to others. So in such instance, it is not always advisable to speculatively execute tasks, as it would unwantedly take up cluster resources. You can enable and disable both map and reduce side speculative execution using these properties: MapReduce map speculative and MapReduce reduce speculative. So whenever you see a lot of tasks that are getting killed, not failed, getting killed, it means the speculative execution might be in play, and those killed jobs might be using your cluster resources. So keep an eye out for that. Let's move on. With the introduction of Yarn, application master can choose to run the job entirely in a single JVM if the job is considered small. This is not always beneficial, but let's look at it just in case if you run into this scenario in your job. If the job has less than 10 mappers and 1 reducer, the job is considered small, and application master will think that creating separate containers for mappers or reducers would take a lot of time as compared to execute them on the same JVM as the application master. This is referred to as Uber execution. In most cluster, Uber execution is disabled using MapReduce job Uber task enable property set to false. By default, a job is considered small when it has 10 mappers and 1 reducer, but you can configure those numbers using MapReduce job Uber task max maps and MapReduce job Uber task max reduce. So to summarize, we saw a lot of properties in this lesson, and we also saw the symptoms or scenarios where you can actually apply those properties to improve performance of your MapReduce execution. Finally, we saw 2 important concepts: speculative execution and Uber task, which might explain some of the performance issues or unwanted resource utilization in your cluster. With that, let's wrap this lesson. See you in the next lesson.